Hello, everyone. I want to give some directions on how to work on a tutorial which I canceled the class, motion in 2 dimensions. So on the first page in the velocity part 1, velocity, they're asking you to graph an oval. And on this oval, choose a point O, which is going to be our origin, and pick up 2 points, A and B, around 1/8 of the oval distance. So that's going to be my point A, that's going to be my point B. Now they are asking us to draw a position vector A. What is position vector? Position vector connects origin to the point. So that's going to be my position vector A. Well, I don't know, like I'm going to label it as A. I can use it also DA, position, sometimes labeled as S and sometimes as D. For position vector B, I'm going to connect origin to the point B and label it as B, right? Now, what is going to be displacement between A and B? Well, it's going to be a arc between points A and B, but for the vector, we are going to just connect vector A, the end of vector A and end of vector B. That's going to be displacement. That's from the object, the car moved from point A to point B. Well, I also don't know there is going to be specific labeling, or I'm just going to label it as A, SAB. So that's going to be the displacement. Now, what kind of questions they are asking us? For example, now if you want to find the average velocity between points A and B, how are we going to do it? Well, generally speaking, we remember that velocity, average velocity, it's what? Well, I would say average displacement divided over interval of time which this displacement was happening. Here, we are going to divide the vector SAB over amount of time. We don't know how long it was, but we do know that if we divide the vector by some number, we are still going to get a vector in the same direction, different magnitude probably. I'm going to assume that delta t was about 2 or 3, and then velocity vector is going to be same direction as displacement vector, but maybe a different magnitude. I'm going to draw it's over here. So velocity vector is parallel to displacement vector. I'm going to label it. And well, magnitude depends on how long it took from point A to B. If it took 5 minutes or 5 seconds, it's going to be 5 times smaller. If it took 0.1 second, it's going to be 10 times longer. Okay, now guys, the idea is to get eventually not average velocity, but instantaneous velocity. Instantaneous velocity, it's a velocity in a certain moment of time. How we can do this? We can choose point B somewhere close to point A. They are telling us label it B prime. Then displacement vector is going to be slightly different, right? It's going to be like this. And velocity vector, because it's parallel to displacement, is also going to be different. If we choose point B closer to point A, so we move it this direction, like over here. Eventually, these 2 points are going to be very close, and displacement vector is going to be almost perpendicular to position vector. Eventually, these 2 points, A and let's call B prime, are going to merge, and instead of a secant line, which we have over here from A to B, it's going to be a tangent line. So eventually, I'm going to make it in gray. We are going to have a velocity or displacement as a tangent line, and it's going to make 90 degrees with position vector. The idea is to kind of understand it from the picture. We see that when point B moves closer and closer to point A, velocity vector or displacement vector, because displacement is parallel to velocity, is going to become more and more perpendicular to position vector. And eventually, they are going to make 90 degrees angle between the position vector from point O to point A. Well, we can actually label it a vector OA, position vector. It's going to be perpendicular. I'm going to write it down, perpendicular to displacement vector. Well, I'm going to label it A, B prime. And because displacement vector is perpendicular to velocity vector, parallel to velocity vector is going to be parallel to velocity. So the idea is that we have to find this. Now, guys, I think what you can do, you can answer the rest of the questions from the velocity part by yourself. And I'm going to move to the acceleration now. So let me scroll it a little bit up. And they want us to draw one more ellipse. I'm going to label it a part 2, acceleration. And part 2 is acceleration for the motion with constant speed. I'm going to just write down with constant speed. Well, there are going to be two different cases, with constant speed acceleration, with constant speed, and acceleration with like non-constant speed. Again, guys, I don't want to draw the whole ellipse. I'm going to just draw a part of an ellipse, something like this. Okay. And well, I'm going to still choose somewhere point O, which is going to be my origin, and point, they are asking to choose points C and point D. They're not telling to choose too far away from each other, so points C and D. We already know that velocity is going to be perpendicular to position, so that's going to be velocity at point C. And over here, we are going to have a velocity at point D. Also, well, perpendicular to, well, mine is not that super perpendicular, actually. Let me kind of correct it a little bit. It's going to be a tangent line to the curve. So tangent line, sorry, tangent line to the curve. Okay, tangent line to the curve over here. So now they are telling us, why don't we copy or kind of draw the velocity at point D from point C? And I'll try to make it parallel. So I'm just copying this velocity. But I did it a little bit kind of something like this. That's going to be velocity at point D. And find the change of velocity. What is change of velocity? Well, velocity C is initial velocity. We're going to add a change of velocity vector to get velocity D. So basically VC plus change of velocity is going to make up VD. So what we'll need to add to VC to get VD, I'm going to graph it in a red color. That's going to be the change of velocity, delta V vector. So we add this plus this, a triangular way is going to produce VD, right? So now they're asking us about the angle. I want to clarify which angle they mean. I'm going to increase a little bit my picture and kind of label in green the angle they're asking about. They're asking about this angle. You see that this angle is less than 90 degrees. Why does it happen? Because we have a motion with constant speed, means that this vector and this vector are equal because speed is constant. That's not changing the magnitude of the vector, which means that the triangle is going to have same sides and that this angle is going to be like, well, different from 90 degrees, but it's going to be like less than 90 degrees. It cannot be greater because there's supposed to be the second same angle and the third one, and all three of them supposed to do 180 degrees, which is not possible if they both are more than 90 degrees. What is going to happen to this angle, which is less than 90 degrees, when the point is going to get closer and closer? The point D moves closer to point C. Well, you see that this vector is going to be less and less different. I'm going to draw my picture of vector VC and VD over here from this point, but you're going to see that eventually the vectors are going to become closer and closer to each other just because the points are closer. And this delta V vector is going to be much smaller, like shorter one, right? And eventually these two vectors are going to merge together and this angle is going to become 90 degrees. Right now it's very close to 90 degrees, still less, but it's going to become 90 degrees. So the idea here is to show that vector of change of velocity is perpendicular to the vector of velocity if the motion happens with constant velocity, okay? Perpendicular. And we know that acceleration, it's a change of velocity divided over change in time. Change in time is a scalar, so we're actually going to have vector of acceleration parallel to vector of change of velocity. I'm going to label acceleration is going to be parallel to the change of velocity. So it means that acceleration in the motion with constant speed is going to be kind of perpendicular to velocity and going to point toward the center of motion. You see? Okay. Just like you can answer the rest of the questions on your own, but I want you just to understand the like ideas they're asking. Now, guys, I'm moving to part 3, acceleration for motion with changing speed. So that's part 3, acceleration for motion with changing speed. What is going to be the difference? Well, they are telling us that the object is speeding up. Again, I'm going to draw a part of like curvy trajectory. What is going to be the difference between the case when it's not speeding up? Again, I'm going to choose 2 points, and my points are going to be E and F. And I'm going to draw velocity at point E, VE, and velocity at point F, which is going to look like this. Well, my velocity at F is bigger because they're asking us about speeding object. Like in the beginning of the paragraph, they are telling that object is speeding up. So VF magnitude is greater than VD magnitude. Speeding up. Object is speeding up. Okay, now, if we draw these 2 vectors from the same point, I'm going to copy as much as I can my vector VF over here. And then we draw the delta V vector. Delta V vector is not going to have 90 degrees angle anymore, right? You see that delta V vector actually has the angle over here between VE and delta V and VE. Angle theta is more than 90 degrees. Why does it happen? Because VF now is longer than V. They're not equal anymore. And if we bring the point closer and closer and closer toward E, this point F, we move it in this direction, it's still going to be kind of greater a little bit. It's going to maybe get closer to 90 degrees, but it's still going to stay greater. Well, I want to just discuss a little bit the ideas of accelerated motion with changing speed. And I want to do it on a circle. I want to do it on like just any curvy trajectory. So just one more word, and I think the rest you can do on your own. But when the velocity of the object is changing, for example, it was moving like this fast, velocity at point A was like this, and velocity at point B is like this. If we draw them together like we did, I'm going to copy, that's VB, right? What we can do, guys, actually we can represent the vector delta V, which is going to be the change in velocity, which is going to be eventually producing acceleration. We remember that acceleration is that delta V divided over delta C. We can split this vector delta V into 2 vectors, one perpendicular to velocity going like this, and one parallel to velocity going like this. These 2 vectors are actually going to describe how velocity is changing. And this perpendicular vector is going to describe rotation of velocity. So velocity was like this, and now velocity is like this. So velocity moved this direction, and this vector is describing it. We are calling this also centripetal acceleration, right? The part of change of velocity, which is, I'm going to label it in green over here, is going to show us how velocity is changing in magnitude. So it was, for example, 2 meters. Well, it was like this. Now, the magnitude of the vector, if I draw it, just the magnitude, not the direction, is going to become bigger. So this green part is describing how much bigger is it. So acceleration is going to consist out of 2 vectors. First one is going to describe the change of velocity as rotation as a vector, moving it down or up, right? And the second part is going to describe whether this vector increasing or decreasing. And we call them normal and, let me actually use correct colors, normal and tangential components of acceleration. So this acceleration, which is perpendicular to velocity, is called normal component. And the green acceleration, which is describing how much velocity is increasing, Well, this is delta V, but we remember that delta V is eventually going to produce acceleration. That's going to be called tangential acceleration. So usually tangential acceleration is parallel to velocity, and it's just stretching the velocity vector, and normal acceleration is going to rotate it towards the center of the curvature. You guys can use these ideas to answer the questions on the last page of the tutorial, page 4, and they have different trajectories, like peanut-shaped and circular trajectories, and one is speeding up and one is kind of a circular. Again, remember, when the object is speeding up, the velocity changes two ways. It's rotating with the angle and increasing by magnitude. When motion happens with constant speed, means that velocity is same 2 meters per second around all the trajectory. The velocity is only rotating. There is still change in velocity. So there is still going to be acceleration, but this acceleration is going to just kind of rotate velocity in different directions, make it up or down. Okay, that's all. I think you can do the rest on your own, answer other questions on your own and do the homework. I'm going to post PDFs of the tutorial, use it for writing and submit it on Canvas. I'm going to post homework, problems 1 and 3, and I'm going to post a pre-test. And you can submit everything in the same assignment. I'm just going to look through all of them, okay? Thank you very much. And I'm sorry that you missed the class today.